Look at our world from space. Those shimmering lines of light aren't just cities. They're the arteries of our civilization, our power grids. We're on the verge of connecting these national arteries into a global supergrid, a vast network of high-voltage direct current, or HVDC, lines spanning continents. The promise? Abundant clean energy, shared across the globe. But this grand vision carries a dark undercurrent, a question that keeps engineers and strategists awake at night. Could a global HVDC supergrid survive a full-blown cyber war? This isn't just about engineering, it's about geopolitics, national security, and the future of our connected world. Let's break down what we're talking about. Today, most countries operate their own national power grids. They're complex, but they're largely self-contained. When a problem occurs, say a power plant goes offline, the disruption is usually confined within that country's borders. Now imagine an HVDC supergrid. Picture a seamless electrical network linking Europe, Asia, and Africa. A solar farm in the Sahara could power homes in Germany. Wind farms in the North Sea could power factories in China. It sounds like a utopia of energy sharing, but here's the catch. In an interconnected system, failures also travel without a passport. A fault in one nation's grid could cascade, creating a domino effect that destabilizes grids thousands of miles away, crossing political borders in milliseconds. The very interconnectedness that makes it so powerful also makes it incredibly fragile. This brings us to the hidden vulnerability, the single point of failure that isn't made of steel or copper. Trust. To make a cross-border supergrid work, nations must trust each other's equipment and operators. Think about it. The complex control systems, the converters, the circuit breakers, they all run on sophisticated software and firmware. Who writes that code? Who gets to update it? Does a foreign utility have remote access to a critical substation inside your country? What happens when political tensions rise between two nations that share a power connection? A malicious actor, whether a state-sponsored group or a sophisticated cyber-terrorist organization, could exploit this trust. They could insert a hidden backdoor in a piece of hardware or launch a targeted attack on a control center. A few lines of malicious code could be enough to manipulate voltage, create instability, and trigger a cascading blackout that plunges entire continents into darkness. The trust required to build the grid becomes its greatest weakness in a conflict. So how do we protect such a system? You might hear talk of cyber immunity or creating a completely unhackable grid. Let's be clear, that is a myth. In the world of cybersecurity, there is no such thing as a 100% secure system. Any connected device can be compromised. The goal isn't absolute immunity. It's resilience. Cyber resilience means designing a system that can withstand an attack, degrade gracefully instead of collapsing, and recover quickly. It means that if one part of the grid is compromised, it can be isolated automatically, preventing the problem from spreading. This is where autonomous local control becomes critical. Substations and regional grids need the intelligence to operate independently if they lose connection to the central command, maintaining power for local communities. And crucially, resilience means keeping a human in the loop. As smart as our automated systems get, final decision-making authority in a crisis must rest with skilled human operators who can understand the broader context and make judgment calls that a machine cannot. Building this resilience requires more than just clever engineering. It demands a global effort from the people who run our grids every day. Walk into any modern grid control room, and you'll see highly trained operators monitoring seas of data, ready to respond to threats in an instant. Their expertise is our first line of defense. We also have international standards like IEC 61850 for substation communication, or NUC-CIP in North America, which set baseline security requirements. But these standards are a starting point, not a complete solution. They are often slow to adapt to new threats. True security will only come from unprecedented international cooperation. We need secure channels for grid operators around the world to share threat intelligence in real time. If an operator in one country detects a new type of malware targeting their grid, they need to be able to instantly warn their counterparts across the globe. This kind of collaboration, building a collective defense shield, is our most powerful weapon against a common threat. It's about moving from a mindset of national secrecy to one of shared survivability. So where does that leave us? Let's face reality. The dream of a global supergrid, powered by clean energy, is powerful and inspiring. It offers a tangible path to tackling climate change and providing energy for all. But as we build this interconnected future, we are also dramatically expanding the potential attack surface for our adversaries. We're creating new digital vulnerabilities on a scale never seen before. The question of whether this supergrid can survive a cyber war isn't just a technical one. Its survival will ultimately depend on a delicate balance. A balance between brilliant, resilient engineering and a new level of political maturity and international cooperation. We need to build a grid that is not just physically strong, but also politically robust, founded on verifiable trust and a shared commitment to keeping the lights on for everyone. The vision of a resilient, interconnected world is within our grasp, but only if we build it with wisdom, foresight, and a healthy dose of caution. Thanks for watching. If you found this exploration into the future of our power grids interesting, be sure to like this video and subscribe to the channel for more deep dives into the technology that shapes our world. Let us know in the comments what you think. Is a global supergrid worth the risk? See you next time.